Right now we're talking about comparing the means and standard deviations of different data sets. We've already talked about case 1, which was comparing a set of samples to a standard reference material. And now we're going to talk about case 2. And in case 2, we are comparing replicate sets of measurements between two data sets. And there's a couple of variabilities here. We could have two different techniques analyzing the same sets of samples. We could have two different days. So I'm going to go through an example and then we'll look at an example from the literature as well. So let's imagine that we were taking some data at the Nisqually River and we were just measuring the pH. And let's say that we had gone down to the river and we picked some sites along the riverbank, and we picked them as sampling sites. Okay, so let's imagine that we take these data points and let's say that we actually take 10 pH measurements, and I'm guessing, I haven't taken this data, but I'm guessing that if we went down there and took some data, we would expect that the river would probably be pretty uniform in terms of its pH measurements. So anyhow, let's go ahead and look at some data. I've made up some sets of 10 pH measurements in Excel, so we'll switch over that right now. Okay, so for now, let's just focus on sets 1 and 2 over here on the left. So I went ahead and made up 10 theoretical pH measurements for set 1 and 10 more for set 2. I calculated the average values down here in row 13 and the standard deviations in row 14. The first question that we have to ask ourselves is whether or not these two data sets can be compared together. So in order for us to group all of these data points together, the first question we ask ourselves is whether or not we can pool our standard deviation values, whether our two sets of data are similarly precise so we can just consider them together. So in order to do that, we take an F-test. So I'm going to switch back over and describe the F-test. There's a bunch of lettered tests in statistics in case you had not yet noticed it. So the F-test, we compare a calculated F value by taking two standard deviations. And in this particular equation, we have to make sure that the first standard deviation, S1, is always the bigger one. Okay, so the big one goes on top. Otherwise, you'll artificially get some really small F values and you won't know if it's real or not. Okay, so from the Excel example for S1 for set 1 and set 2. Switching back over, our two standard deviations are 0.06 for set 1 and 0.10 for set 2. So that means my S1 is actually going to be for set 2, and so that would be 0.10, and my S2 is going to be 0.06, which was for set 1. So when I calculate the F value between these two sets, I have 0.10 squared over 0.06 squared. So go ahead and calculate that through. Pause the video real quick. Hopefully you got 2.78. So this isn't as far as we go, right? We also have to compare this statistical number to something. So in all of our statistical tests, we're going to be comparing the number that we calculate to a tabulated number. So I'm going to switch over to show you that tabulated number here. So as you're looking at it, I want you to look at this table 4.4 and notice that we have columns with degrees of freedom and rows with degrees of freedom. And our two sample sets, we're going to choose the column degrees of freedom for each one. Since we had the same number in both and we had 10 samples, that means that we have 9 degrees of freedom for each. So if we go down to the place where 9 and 9 meet each other, we will get that the F tabulated value is 3.18. So I'm going to switch back over to our work here now and put in that our tabulated value was 3.18. Notice that the one that we calculated was 2.78, which is less than the tabulated value. And in this case, that means that our standard deviations that we just compared with our F-test are statistically equivalent to each other. That is what we conclude from the F-test. It just means that they are similarly precise. Okay? The F-test does not tell us anything about the data sets other than the precision. So because we can consider these two standard deviations to be statistically equivalent, that means that we can calculate a pooled standard deviation by combining both of these. So the equation for that, we take S1 squared times the degrees of freedom plus S2 squared times its degrees of freedom divided by the total degrees of freedom. So for our sample, the pH example that we're doing, our pooled standard deviation is going to be 0.10 squared times 9 plus 0.06 squared times 9 over 18. So go ahead and pause this for a second and calculate it. Hopefully you got 0.08. Hopefully I didn't make math errors either. So when we pool the standard deviation, we now can go ahead and calculate a t-value. So this t-value is going to tell us about whether or not the data set is statistically equivalent, or excuse me, the two data sets are statistically equivalent to each other. So we take the two mean values for the data set, we take the difference between them, but then we get rid of the sign if x1 happens to be smaller than x2, so we just want the absolute value there. We're going to divide it by that pooled standard deviation, and then we're going to take the number of data points in our data sets, take the product divided by the sum, and then take the square root, multiply by that. So we're going to go ahead and calculate all those things, plugging in for our Excel example here. Then we have 7.34 minus 7.29, divided by our pooled standard deviation, which was 0.08, square root of 100 divided by 20. So go ahead and pause and plug that through, and you should get 1.40 for your calculated t-value. Now, just like we did with comparing the F-test, we're going to do this t-test comparing the calculated value for the t with the tabulated value for the t. So here our degrees of freedom are just 18. So if we go back over to that table, we can see that we don't have 18 degrees of freedom on the table. So instead, if we look at n equals 15, the t, we better pick a confidence level, right? So let's go with the 95% confidence level again. So our t is 2.131 for n equals 15. And if we look at n equals 20, t is 2.086. So both of these are larger than our calculated value, switching back. So our calculated value is less than that t-table value. I'm going to go ahead and write those two values in. For 20, it was 2.086, and for 15, it was 2.131. So because our calculated t-value is less than our tabulated t-value, that means that at the 95% confidence level, our sets 1 and set 2 are statistically equivalent. Okay, so I want to reiterate something real quick here, which is that when we do the F-test, what this tells us is whether or not the standard deviations are similarly precise. It just tells us about the precision. When we do a t-test, this is the one that tells us if our data sets statistically equivalent. So usually we have to do both sets. Okay, both sets of calculations, the F-test and the t-test. Okay, so this is a nice example of a pair of sets where this is case 2 analysis that we've been doing. We were able to pull the standard deviations, and we found that our sets were similarly precise when we did the F-test and statistically equivalent. So let's go ahead and look at another example. So I'm going to switch over to Excel again. And when we look at set 3 in comparison to set 1, I set up another set of pH values that have a little bit more variability, and so their standard deviation is a little bit higher. Let's go ahead and calculate the F-test for these two sets. And so pause the video, do the F-test, and then we'll come back together in just a moment. Okay, so hopefully when you calculated the F-test, you found that you can't pool these data, and then you probably said, wait, I can't do the t-test yet because I don't have the same kind of situation that I had before. So let's switch back over and see how to handle it. So for sets 1 and 3, you should have found that F was equal to 5.44, which is greater than that 2.78 or whatever it is, right? So this is greater than the F table, and therefore we can't pool the standard deviation information. So in that case, we just have a new calculation for t. Okay, so if we can't pool, then we use this equation instead. It's pretty similar to the other one. We just actually don't have to calculate a separate pooled standard deviation. So we still take the difference between the means for the data sets, and then we're going to take the standard deviation of 1 divided by its data points, and the standard deviation of the other divided by its data points. We'll add those separately and take the square root. So for the sets 1 and 3, we're going to have 7.33 minus 7.29, absolute value, and 0.14 squared over 10 plus 0.06 squared over 10. So go ahead and calculate this through and pause the video. And hopefully you should get 0.83. So just as we had before, our t calculated was still less than the tabulated value. Now there is a fancy way of calculating degrees of freedom for this unpooled data set. I'm not going to go through it here because you need it very rarely. You can go ahead and still use 18 degrees of freedom for most of your situations. If you have different numbers of data sets, you might end up having to calculate it. But anyway, the calculation doesn't come up that often, and I'm just going to say, if you have to calculate it, look it up in the book. It's in this section 4.3, and you won't have any trouble finding it. Maybe we'll try it a little bit later. Okay, so when we have a situation here, we have still been able to conclude that set 1 and set 3, even though they were not similarly precise, they are still statistically equivalent. So let's take a second to visualize what these different kinds of scenarios look like. So in our first sets 1 and 2, we had 2 samples, and if I drew a Gaussian curve for them, they had slightly different mean values and slightly different standard deviations, but they were pretty similar, and so we probably had a similar situation like this. So they passed the F-test and they passed the T-test. Now, the one that we just had, sets 1 and 3, they too had a slightly different mean, and they had a little more different standard deviations. So we failed the F-test, but we passed the T-test because the 2 means are still in a pretty similar location, right? That's really what we're trying to ask. Are these similar to each other? So if we can imagine a situation where we could pass the F-test, but fail the T-test. So that might look like 2 standard deviations that were pretty similar to each other, but we don't have much overlap between our 2 data sets, that their means are pretty different from each other. In that case, they would not be statistically equivalent data sets. The other scenario that we might have is that we might fail the F-test and also fail the T-test. And so in that case, we would have a scenario kind of like the one we just drew, except that our 2 data sets would have pretty different shaped curves as well. All right, so I think I've covered all of my scenarios here. So long story short, you must do both the F-test and the T-test for case 3, or excuse me, case 2, which is what we're talking about right here. So first you do the F-test, see if you need to pool the data, then you do the T-test, and then you see what happens. Okay, so I'm going to switch back over to Excel, and I want you to go through this scenario for 2 more sets of data. I want you to compare sets 2 and 4. Okay, so here's set 2, here's set 4. Go ahead and calculate the F-test. See if these guys pass the F-test. And then calculate the T and see if the 2 sets are statistically equivalent to each other. So pause the video and go ahead and do those calculations. Okay, hopefully you took time to go ahead and do those calculations. If not, make sure to do them later. So let's look at what the results would be from this comparing sets 2 and 4. When I calculated the F-test, I got a 1.21 for the F-test, which means that it passes the F-test. These guys are similarly precise between the 2 data sets. So when I did the T calculation, I had to pool the data sets. So I got a pooled standard deviation of 0.11. And then when I calculated the T, I got 6.50. Now, I know that my table value was approximately 2.1, which means that sets 2 and 4 are not statistically equivalent, and we cannot just assume that these are two equivalent sets of pH values. Okay, so this whole video has been talking about case 2 as a way of comparing the means and standard deviations for two similar data sets. And I'm not going to assign an assignment yet until the next video after we have also talked about case 3. So go ahead and finish up this video, go back and do any calculations that you might have done, and if you're finished with those, then you can move on to the next video.